Hello everyone, welcome to the video presentation of group number 2. So the topic we have chosen is SuRF practical range query filtering with fast succinct tries. So in this particular video presentation we have tried to divide the important and the most basic sections into 6 different parts to clear understanding, and so that it's easier for us to explain, and thus it's easier for the audience as well to understand what the particular topic is and what is the use, when is it used, and how we can use it even better. So in this particular section we'll be talking about fast succinct tries, so which is also called as FST. So the FST is SuRF's primary data structure. SuRF is like the succinct range filters. It's a static tree that responds to point and range queries in a small amount of space. The architecture of the FST is based on the fact that the highest levels of tree have a smaller number of nodes but a larger number of access, and the majority of the nodes are found in the lower levels, which are also the colder levels. We choose performance above space by encoding the upper levels using a fast bitmap based encoding approach, which is also called as Louds dense, in which a child node search requires just one array lookup so that the overall size of the encoded tree is constrained. We use the space efficient Loud sparse technique to encode the lower levels. So in this particular slide we'll be talking about Louds dense and Loud sparse and their operations. So LoudsDS is a hybrid tree in which LoudsDense is used to encode the top levels and the LoudsParse is used to encode the lower levels. To trade performance and space, the separating point between the top and lower levels can be adjusted. Because of the space efficiency afforded by LoudsParse, the FST, which is again the fastest tree, keeps the number of upper layers modest. So to identify the dividing point between these two levels, which is again a very important part, we maintain a size ratio R between loud sparse and loud dense, so that we can easily identify which is the upper section and which is this lower section. The LoudsDS mainly supports 3 different operations, which is done really efficiently in this particular case. So the first one is exact key search. So this particular operation returns the value of the key if the key exists, or if it returns null otherwise. So the second operation is lower bound key. So this particular operation return an iterator pointing to the key value pair, which is like k or v, where k is the smallest in lexicographical order, satisfying k is greater than the key. And the next operation which LoudsDS supports is, it really supports efficiently, is move to next iter. So this particular operations move the iterator to the next key value. So the next slide will be explained by my friend Ramit. So I'll take you to the next slide. Thank you.
Thank you, Arpit. Now I'll be going to explain what are second range filters and what are its types. So first is the SuRF is a fast and compact filter that supports exact matching filtering, range filtering, and estimated range counting. For point and range membership tests such as Bloom filters, SuRF ensures one-sided mistakes. SuRF can trade off false positive rate and memory usage, and this trade-off is semi-independently configurable for point and range queries. SuRF is based on the fast second try, a new space efficient data structure. SuRF's main idea is to convert the FST into a rough membership filter by removing levels from the tries and replacing them with a set of suffix bits. So in this slide, I'll be talk about the types of SuRF filters. There are basically 4 types of filters. The first is the SuRF base. Second one is the SuRF with hash key suffixes. The third one is SuRF with real key suffixes, and the last one is SuRF mixed. So we'll start with the first one, SuRF base. It is the most basic form of SuRF that contains the minimum length key prefixes required to uniquely identify each key. Beyond the common prefixes, SuRF base simply keeps an extra byte for each key. The second one, SuRF with hashed key suffixes, that is called the SuRF hash. It reduces the false positive rate of SuRF base by just adding a few hash bits per key. The third one, SuRF with real key suffixes, that is also called real SuRF. It stores the n key bits right after the key stored prefix. Although SuRF real improves FPR for both point and range queries, utilizing real keys for suffix bits cannot provide as good FPR as hash bits because the distribution correlation between the stored keys and the query keys lowers the distinguishability of the real suffix bits. The last one is SuRF mix. The SuRF mix has a mix of hashed and genuine key suffix bits. The suffix bits for the same key are stored sequentially so that a single memory reference can obtain both suffixes. Now, my friend Shivam will explain the next slide, so I'll hand it over to him.
Thank you, Ramit. Now I am gonna explain FST evaluation. So first one is FST versus pointer based indexes. So in this, the most prevalent index structure in database system is the B plus tree. To compare against FST, we employ the fast STX B plus tree. For the best in memory performance, the node size is set to be 512 bytes. Only fixed length keys were used in our test. Now, that is art. Adaptive radix tree. The adaptive radix tree is a cutting edge index structure for in-memory databases. To improve cache memory performance and space economy, art picks from 4 distinct node configurations based on branching density. See art. We developed a compact version of art by transforming a regular art instance to a static version. Now next is FST versus other second try. This is a Louds based open source concise try implementation. Its concept is similar to Louds parse, but however it lacks the section to optimization. A state of the art concise try implementation based on DFUDS is the path decomposed try. VDT used the path decomposition technique to rebalance the try and resulting in the reduced latency and space.
So in this particular slide, we'll be concluding our presentation, and I'll be talking a few things which we have discussed in our previous slides and try to put all in all and in a single slide. So just a bit of idea, okay, that what we have talked before. So SuRF is built upon a new succinct data structure called the fast succinct tries (FST), which you might not know already by now. So that requires only 10 bits per node to encode the tries. The FST is engineered to have performance equivalent to state-of-the-art pointer-based indexes. The SuRF, which is again succinct range filters, is memory efficient, and its space/false positive rates can be tuned by choosing different amount of suffix bits to include. We use FSTs because again, as I discussed before, it is really space efficient. So and it answers point to point to range queries, and it is much faster. If I specifically, so it is 4 to 15 times faster than the earlier trees which use the other tree representations. It also achieves performance better than the pointer based indexes, which are considered the state of art indexes. And that is the reason we use the data structure FST in this particular case. We also believe that the SuRF is a promising technique for optimizing future storage systems, and it can be really helpful to improve the performance as well as the speed and a lot of things in the future as well. Thank you everyone for giving your time, taking your time out to see our video presentation. I hope you guys liked it. I hope you guys understood what we're trying to explain, and I hope that our video presentation interested you a bit to go further into the deep reading, and you guys can explore the topic. And I personally feel this is a very interesting topic. So thank you again. Thank you so much.